Welcome to the pre-laboratory video for the second experiment. I hope you enjoyed carrying out the previous experiment with a more physical approach to this topic area. But now we're going to look at why we see a quantization of energetic particles by looking at where light comes from, and we're also going to look at the interaction of light with chemical systems. This experiment involves two parts, which should be familiar. We have a simple flame test of lithium, sodium, and potassium ions, followed by a metal complexation reaction demonstrating a few colored cobalt-2 complexes. These experiments may seem very simple, but your aim is to use the concepts learned from the previous experiment while carrying these out. We're going to represent the atom in a few energetic forms throughout this video, which might be quite confusing for some of you at first. But I want you to bear in mind that this is just an alternative way of describing molecules by just thinking about their electronic structure and uses the energy of the electrons as the focal point. Now, this doesn't mean that any previous representations of looking at atomic and molecular structure are wrong. They are still very valid. They're just focusing more on the molecules in space to predict reaction. This model is just thinking of the energies of the electrons instead, as this information is very useful when predicting thermodynamic aspects of a reaction process. It's just another tool you can use to try and explain your observations. By describing an electron in its energetic form, we can represent its interaction with electromagnetic radiation, as this is just a representation of energy transfer, remember. This energetic exchange is a very large part of describing chemical reaction. So as these experiments concern interaction with visible light, we're just going to go over visible light in some brief detail. So as we know, the term visible light describes an energy range of electromagnetic radiation. The different colors correspond to different wavelengths of light, or this can be described as a stream of photons with a certain energy. For example, blue light is typically 450 to 495 nanometers, meaning that the photons in the stream of blue light are typically carrying the energy of 4 to 4.5 times 10 to the minus 19 joules. Red is of a higher wavelength, typically around 620 to 750 nanometers, meaning the photons of red light carry less energy. This is typically 2.7 to 3.2 times 10 to the minus 19 joules. These terms of energy and wavelength can be used interchangeably to describe light, as they are directly related. They both convey the same thing, the energy of the electromagnetic radiation. Here is a simple energy level diagram that represents energies of electrons according to only their principal quantum number, but not looking at the individual orbital energy differences within the shells that this principal quantum number represents. The energy differences seen between each principal quantum number, or shell of electrons, are the biggest energy differences within an atom's quantized states. So we're assuming that all the orbitals within each shell, for example, the 2s and the 2p orbitals within the second shell, are all the same energy because we're focused on a larger energy difference. The orbitals that electrons occupy then are also thought to be quantized, meaning that the electron, like a photon, can only exist at certain exact energies. Now, this diagram can nicely demonstrate the phenomenon of emission, which will show that the quantized energy levels produce quantized photon energies as well. Emission involves the production of light, or the production of photons, by exciting the electrons to a higher energy level, by heating the atom, for example. Once excited, the electron wants to return to the more stable energy level of lower energy. To do this, though, there needs to be a conservation of energy, so when the energies relax back down, they emit a photon that's equivalent to this energy gap between the two quantized energy levels that the electron is transitioning in between. We will observe light if this energy gap lies within the energy range of visible light. The color of this light emitted is determined by the energy gap as well. For example, the light will be blue if the energy gap lies within the range of 4 to 4.5 times 10 to the minus 19 joules, as was mentioned earlier, that this is the energy range of photons corresponding with blue color. When carrying out your experiment, bear in mind that there could be multiple electronic transitions within a single atom. The electron could be promoted from the first principal shell to the third, for example. Think about the impact this will have on the energies of the photons and the color of the light emitted. So we're going to look at another energy level diagram to explain the absorption of light in transition metal solutions. Now, this is a representation of the orbital energies within a single shell of electrons. So in this case, it is showing the d orbitals only within the third principal shell. And each horizontal line represents an individual 3D orbital. So in this diagram, we're now accounting for differences in energy between orbitals within a principal energy level. In this case, the orbitals are different in energy because of crystal field splitting. In this example, there's only one electron occupying one of the d orbitals, which we have now represented with an arrow to show its spin, but it doesn't actually matter in this instance. It's just a representation of an electron. So I'd like you to have a look at this image of a clear blue solution. Now this solution isn't blue because it's emitting blue light. It's actually blue because it's absorbing the photons of energy opposite to blue. So what I mean by this is there'll be a white light shining on the solution. And a white light means that it carries the entire range of energy across the visible light spectrum, from 400 to 750 nanometers. The energy of this light will be able to excite electrons to higher energy levels if the energy gap between the levels is equal to the energy of the photon. But in the case of absorption, when the electron returns to its stable ground state from the excited state, it will not conserve the energy by emitting a photon equal to the energy gap, but the energy will be lost in a non-radiative form. This could be as vibrational energy, for example. This will leave the photons of all energies that were not absorbed to pass through or reflect off the solution. In the case of a blue solution, the photons absorbed will be of energy that corresponds to the complementary color to blue, which is orange. This can be seen in the color wheel, where the complementary color is shown as being across the wheel. So that has covered the interaction of electromagnetic radiation in chemical systems through looking at absorption and emission. This should prepare you to answer the questions throughout the experiment when you do it, and I hope that you're now more comfortable with representing electrons and their orbitals in energetic terms now. And you can appreciate the orbitals they exist in are quantized in energy, and then this relationship to electromagnetic radiation. I'd like to show you one more energy level diagram in this video before we finish though. So here we're looking at a simplified energy level diagram that's just showing the energies of the HOMO and LUMO orbitals. This is exactly the same as the other energy level diagrams we looked at in this video, but we're now just looking at different orbitals. So you'll know from your course that the HOMO means the highest occupied molecular orbital, and this is usually a bonding orbital, and the LUMO is the lowest unoccupied molecular orbital, and this is usually an antibonding orbital. So each horizontal line here is representing one molecular orbital that contains two electrons within it. This representation of molecular orbitals is mainly used to describe covalently bonded molecules. So two atomic orbitals have combined together to form a bonding and anti-bonding molecular orbitals, with an energy gap in between. I'm showing you this because I want you to see that we can describe various electronic characteristics using this energy level diagram format. And also because I want to highlight this HOMO-LUMO energy gap and how important it is to predict chemical behavior. In the case of a sigma bond, when we have the HOMO as a bonding orbital and the LUMO as an antibonding orbital, this HOMO-LUMO gap is very useful to predict the bond strength. If we have a small gap, it will be easy to break the bond, as it will be easy to fill the antibonding orbital. A large HOMO-LUMO gap will represent a strong covalent bond, as the energy required to promote an electron to the antibonding orbital will be higher. This is going a bit beyond what you need to know in your course, but I think it highlights how useful it is to view a molecule in its energetic terms to predict chemical behavior. That concludes this video, and just remember it's much easier to think of a molecule and its electrons in energetic terms to relate to its interactions with energetic particles of electromagnetic radiation. And also that this is a very useful tool to describe thermodynamic properties of atoms and molecules.